Anímeme a esto. Mira, es que...
No anda la placa de Windows. Ahí está, esa no va. No, dale a cualquier página, no HTTPS, dale cualquiera. Google.com, pero sin HTTPS. Esa por ejemplo.
Cierra el navegador.
Ahora, completar, yes. Listo, ya está.
Bien. Perfecto. Okay. Sorry for the delay. I'm sorry for that, but it was some problem with the connection of the Wi-Fi. Okay. So I don't make a presentation because I wanted to show you the documentation of the Kratos, because I think that it's something important, not only the not only the documentation that you already have it by the Flash, but also go to the wiki of the Kratos. So the Kratos wiki, which is the Kratos wiki in simnet.upc.edu, you can, if you search it by just Kratos and wiki, you would get the Gods of War game. So this is not what you are looking for. So you have to look for Kratos, Simne, and wiki, and you will get this wiki page. Here you can see that clicking here, you can go to the main page of the Kratos, but it's not the intention right now. You can go to some shortcuts, like to the how-tos, which is quite interesting because many documentation of the Kratos are there, like in general about installing, about OpenMP parallelization, MPI parallelization, OpenCL, Python, how to do the input-output, in C++, many of them. So here you have many of the questions that you may got just in the time of the programming. You can go here. Turning back, here you can go to the repository of the Kratos. So it's saying that what is the repository, and you can even go through the directories and you can see what is the version of the repository at the moment. Sometimes you change something and you said, okay, something is not working. Let's see what has changed. So it's one of the ways. Then I would suggest you to go to the what is Kratos you already know, so it's not a problem. Then we have some documentation. Here against the how-tos, the Kratos for Dummies, that this will be the starting point for just to create a new application and writing a new element. My colleagues will talk about it afterward. Then there are some Kratos tutorials, which starting from the Git interface, the Kratos structure, this is the basis of the presentation before. And then you have the Python scripting. Actually, I will do this tutorial right now. So it's quite easy. These are about 6-step tutorial. That's just very basic things that you need just to modify, to put some new boundary condition, changing some elemental value or nodal value, these kind of things, reading some input data and writing some data. So this is the basic things that you need just to understand if you want to open a Python script of Kratos and you want to understand something, so you should know the things. The first point that you have to do for nearly every program or every Python script that you want to do for Kratos is this one. The syntax of from something import all is from Python. This is not something of Kratos. But here we are saying that load the module of Python of Kratos. So this is the Kratos multiphysics core, nothing more. By loading this, you just have some I/O, some data structure, but you don't have any physics, because the physics are in the applications, and you will see how to deal with that. If you run this and you put the hello, at that time it was the Kratos version 3, so right now it's Kratos version 4. So if you want this to run, we assume that you have the developer installation of the Kratos. So you have in the Python path somewhere that where is pointing to your Kratos. If you have installed only by Git, by some tricks achieve to do this just to putting a Python path equal to the path of the problem type. But it's not the usual way, because the people who download it for using in Git, they don't want to change something from Python. Then we have the next tutorial, that is how to creating and reading a model part. So you have an input file considering, and you want to create something. Here we start again. Start with from Kratos Multiphysics, import everything. And now, because I want to open some files, so I need some elements, and elements usually they have some physics. So I have to import the physics of or the application that I wanted to work with that. In this case, I just wanted to work with the solid mechanic application. So it's from Kratos dot solid mechanic application, import everything. If it's the fluid dynamic application, so it would be from Kratos Multiphysics dot fluid dynamic application, import everything. Okay, so do you want me to put it larger, the font size, or you can read it? It's okay? Okay. Then we need to create a model part. This is another standard part of the many scripts in the Kratos. First of all, you have to call the constructor of the model part. It means in the Python language, it means that you have to read, this is the variable that I want to create, equal to calling the model part, parentheses, and you give it a name. The name is actually it's just an information. You don't use it to look for that afterward. But when you print some model part, it says this is model part, a structure model part, and they start to writing the number of nodes, element, and this kind of thing. And here you can see, for instance, I said print structure model part. I said this is the previous, this is the 2.7 Python version. So in the new one, you have to put parentheses. And I would change this. So it says that this is the structure of a structure part model part. So the name is a structure part. Then the buffer size is 1, number of tables 0, and everything is 0. So it's an empty model part you have created. You can add, first of all, after creating the model part, what you have to say is that what are the nodal variables, the historical nodal variables. You remember that Miguel Angel was telling this before, that in the nodal solution step, you have nodal solution step and nodal get value and set values. So for solution step, you have to describe in the Python, in the beginning, which variable you want to store. And the way is to add nodal solution step variable, for instance, displacement and force, because I want to work with that. If you are in fluid, usually here you have to put velocity, pressure, don't know, viscosity if you want to store it nodally. So the list can be quite large in some applications. And usually each solver has its own. So you just call the add nodal solution step variable of the solver, but inside something like this. Okay. So the first step is to create model part and saying which variable you want to store in each node. Okay. Second step will be reading the model part, because we assume that you have an external mesh generator that is create a model, an input file like Git, for instance here. So this is a typical input file. You can find the documentation of this input file also in the documentation part of the wiki, that's saying how it's structured. But usually it's a begin end with something, begin model part, and model part is the data. Then begin properties with the ID of properties and say density is this. The vector of the body force is like this. And then you have begin node, end node, the nodes and the coordinates, the ID and coordinates, and the connectivity of the total Lagrangian element to the 3 nodes. It's like this with the properties 1. So it's ID, properties, and the connectivity. You have the nodal data, so saying that I'm putting the displacement x for node 1, and I'm fixing it. The second one is as a fixature to 100. I'm going like this. So I take this example MDPA. So the file of the MDPA says which is the data for a model part. And I'm trying to read this. This is defining this mesh. So, first of all, I just create a model part IO, which is an object in charge of reading a model part from the file. And I'm giving the path to the file of this example as an argument. I haven't read it yet, the model part. I'm just creating the object. Then here I'm saying that to this object that I'm creating, saying that read model part, and I'm passing my structure model part. So I'm passing the structure model part here. It reads this input file and put all these elements, nodes, condition, on an initial value and everything inside my model part. After this statement, I have my model part with all the nodal information. This is one of the standard part. And the third thing is that you have to say how many history or how many time history back you want to store. Here we are saying that I want to store 3 steps. So the current one and 2 steps before. Okay? If you have any question, just interrupt me. Don't wait until the end. So after reading input file, we want to write output file. This actually in the wiki you can find some place here. So it's go to the how to use Git.io, and it's a complete explanation of how it is and how you can use it for writing multiple files in binary, in ASCII, writing the condition, not writing the condition. There are many combinations that is completely described here. But as a very fast and quick introduction, what you should do is that, okay, here we have the part of the beginning that I'm importing application, creating the model part, adding the nodal forces, reading the model part, and now I'm creating the Git.io. The Git.io, that here it says that it's in charge of the writing the result for Git, and it's multiple file flag, write condition or not, they are the combination that you can have. And finally, here you have giving these parameters that use multifile or not, or writing the condition or not, and you create a Git.io. So this you have now an object that you can passing it something to write to Git. For writing, first you can write the mesh. For instance, if you change the mesh, usually you want to write it again because you remesh or you refine or something. So for writing mesh, you give it a name to the mesh. So initialize mesh with this name and then you write it. So it's a structure model part get mesh. So it's writing this mesh down there. And then you need to do a finalize mesh. This is an example. So first you need to initialize mesh with some number, writing the mesh and finalizing it. It's done in 3 steps. This is actually reflecting how Git post library is. And then for instance, for writing nodal data, you have to write, you have to choose the initialize result first, for instance, then write nodal results, displacement, and giving the array of the nodes. So by this statement, you will write the displacement of all of these nodes for the Git, and that's it. And temperature again. So it's quite easy to write your result and visualizing it in Git just using this scripting. And finalize mesh. If you want to write an elemental data, you have to use the print on Gauss point. Then you, for instance, the stress tensor that is already measured and calculated in the Gauss point, so you can write it in, sending this time the model part entirely, and the parameter of the time here also. So you're just passing the time, and for each time because time is actually the stamp that you are putting for this result. So in the Git, it will give you that the second one is this result. I'm going quite fast because we are quite out of time. but you can ask me, and actually this documentation is always in the wiki, so you can reference to it afterward. And I would ask you to do by yourself all of these statements just to see how it works, because then we start to have how we want to access the nodal data, because this is quite interesting for us, because we want to change them, we want to fix them. So this is the common part, just to starting, so you can copy paste this in the script, that's just run, creating the model part. Accessing the node is quite easy, because if you have a model part, so a model part.node gives the nodes of the model part, an array of the nodes. And for loop over the nodes, you can put for node, this is the Python, let's say, syntax, is for node in structural model part.node, print node. So if you do this, it will start to raise your node number 1 with the I don't know things. Or you can say, okay, for all the nodes, print node ID. So it's a start to writing you just the IDs of the node. So that is quite clear and easy to use, and to have a loop for the nodes and do something, for instance. Accessing the coordinate of the node, so it's node.x. Be careful here, it's important to be capital. Python distinguishes between the capital letter and not. So if you put node.x but in not capital form, it's in lowercase, it's not working. Okay. You can write, for instance, the node ID with an x, y, z. So you can write the coordinates of all the nodes, or you can put some if. This is quite interesting, because consider that you are in the input and you can start to put some conditional things. So you said, okay, let's put if the node x is larger than 0.0, so let's do something with that. Here I'm printing, but you can do many things with that. This is really good for academic problems that you want to apply some condition exactly in the plane xy0 or xy5, so you just apply it. Then you can get nodal data. For instance, displacement as a historical value of a node. So it's node displacement is equal to get solution step value of the displacement. If you want the previous step, one previous step, so you get solution step value of the displacement, one solution before, one step before, or two steps before. Then you can go to, you can use the set solution step value, for instance, temperature, in the current step, 0 is the current one, to this value.
So it will set the variation of temperature with respect to time from 0 to 100? What this code will do?
I'm putting the temperature, the variable temperature in this, for all the nodes in this structural model part to 100.
0 to 1?
No. 0 is the current time step. Because you can set this is time step. Reflects, this is the time step starting from current time step. So it's the current time step is the 0. The previous time step is 1 before. Time step before is 2. And 100 is the value that I'm putting to the temperature, or to other variable that we want to put there. Finally, we have the part that we want to access into the elements that is quite similar to the node, so you can get points.elements or conditions, and you can loop over them and do something with the elements, getting the IDs of the nodes or these kind of things. And finally, just for using the solver, there are some steps that we have to have in mind. One is we have to initialize the solver always. So the first thing is that you import a solver and you have to initialize it. This is down here. Let me check it. Okay. Here I'm creating the solver with the structure model part, with the domain size and echo level. Echo level says how many messages you want to get. Then I'm giving some more parameters. For instance, because when you start with the solver, actually, the solver you're creating, it has many default values inside, many of them. That they are the default values that the developers think that it's suit well to many people. If you want to change some of them, what you can do is you go after creating the solver, but before initializing, you have to put some changes. For instance, I want to reform the DOF set in each step because I'm changing the mesh. So I'm putting it to true. The default value was a false. So for this one, first you have to know, you should know the solver, you should know the parameters of the solver. That it's as easy as to go to the solver and open it because it's in the constructor, you can see the list of them and the default value. And you're setting it, and finally you're doing the initialization. Don't change anything inside the solver after initialization because it's not designed for that. So initialization is the point that you said, okay, I configure my solver, I'm initializing it. After that, if you put this true after initialize, it won't affect or it may crash, or this is something that you have to consider. After doing this, then you can solve. Actually. And usually the solver solve calls many things. So finally putting everything together, here we have, for instance, initialize result, a loop for time step here, and something new. What I'm doing here, in each time step I'm saying to the model part that, okay, I'm the current step, I want to move one step more. So please copy all of the data you have in the nodes for the next step. In this part, it will do just this. And the last history that right now is out of scope because you are preserving just 3 of them will be deleted. That's it. So it's just doing this, and you can start solve, writing result, and finalize. This is very simple, but actually many of our scripts are based on this structure. So just knowing this, the rest of the things that they are calling usually are additional utilities, additional functions. There are many of them. There are a script that they are 1,000 lines. But the structure more or less is always the same. Okay? And that's it. So I think that's for the, any question?
If we want to print multiple nodal IDs, then can we apply the loop for that?
Yes, actually what we do is that we start to select them in some array, even in Python, and then we store them. There are several examples of that. And then you can just loop over that array of nodes, that they are very small. For instance, you get the inlet nodes, all of the nodes that are selected. If the node is inlet, so we append it to some list, and then we have the inlet nodes. Then besides putting the 4 over all the nodes, you can put 4 for the nodes in inlet nodes. And then the node is only few ones, so you can set the velocity, you can describe, calculate the normal, or many things. Okay? Any other question? I think that we can. No, please sit down.
I've actually run the Kratos, but there is no menu of Kratos.
Lisa? Okay, hello everyone. I will, oh, this is the wrong presentation. Okay. Okay. Hello, everyone. I will be talking a little bit how to implement a new application. So the problem we're going to solve actually is the easiest we could think about. Is just a heat diffusion problem. So let's suppose we have just 2 elements, but we could have as many as we want. And then we want to see the final result, the final temperature distribution. So, well, as it was said several times before during the day, Kratos has a core that is mainly designed for finite elements. So there are several solvers, linear solvers, iterated solvers, and other kinds of solvers also. There are utilities in case there are some tasks that cannot be done by the solver. And also there are the strategies. That means that we are going to assemble our system. So for example, we just can program our element, and then the core will take care of assembling the whole system of equation. So in our case of just our simple problem, the only thing we have to do is create a new application that only has to contain the elements, because actually all the other tasks that are just normal finite elements can be done directly by the core. So actually you see the tasks involved here is quite small. So how do we create a new application? Well, I forgot to say, if we wanted to add new strategies or new solvers, we could also add it in our application. But actually, we only care about the first 2 steps. So, as I said before again, it's finite element oriented. So the implementation of traditional finite elements is quite straightforward. And also the management of variables is quite easy because it's already implemented there. So actually, we won't have to care about this. The core will take care of that. So if we take a look at a new application, we'll see all these folders. So we have the constructor, the main files, the pure diffusion application in this case, because it's just the name that I gave it. The elements that are the one that we're going to program. Ricardo will show you later how it's done. Utilities, if we had, but if we don't, it's fine. We don't add anything in this folder. And also the Python scripts. It's interesting to notice that if you want to create a new application and you don't want to do any programming, you could also do it. You could just create a new application that does nothing but only contain Python scripts. It would be possible also. So what are the tasks that we have to do to create our to solve our problem? Well, we have to get the data from the input file in the way Puyan you do before. We have to add the variables, define the degrees of freedom, generate the stiffness matrices, and assemble them, and finally solve the system and print the results. Okay, so how do we create a new application if we want to create a new one and there's nothing similar to what we want to do? Okay, we can go to this tutorial page that is in the wiki of the Kratos and follow the steps. But basically, it consists on downloading an empty application that is called test application, and then we rename it using a script file that is provided in the same folder. So actually, you only have to define the name of the application, and automatically all the names inside of this folder will be changed. So for example, I started with this test application, and by just executing this command, I got all the files renamed to the new names. So actually, you don't have to care about renaming everything. It will be done automatically. You just decide your name, and it's done. Finally, we also will have to modify the Kratos core to tell Kratos, okay, I have a new application, and I want you to compile it. So how do we